So let's consider an example now. We're looking at this vector space F. We've talked about this vector space before. This is the collection of all real valued functions defined on the open interval from A to B on, let's say, the x-axis. And so that's a known vector space. We checked that recently. We're going to consider now a subset of that vector space. Specifically, here we go, it's the collection of all vectors in that vector space F that have the property that the value of the function is equal to 0 at the midpoint. And you'll notice here I'm using m to represent just the midpoint of our interval. Okay, so certainly some functions in F have this property. Most don't, but some do. Those who have this property that at the midpoint they're 0 are in our new set W. And the question is, we want to ask, is this W a subset of F? Is that also a subspace of F? So to address this question, we're going to go back to the theorem that we proved in the last recording. And that is, if you have a non-empty subset of a known vector space, all you have to check is that non-empty subset is closed under addition and closed under scalar multiplication. You have those two properties and you're good. This set is a subspace of the vector space V. And then, of course, what that means is that in addition to that, it's also a vector space on its own. So let's apply that idea here. Is this set defined like so, is that closed under addition? This is the first question we have to ask. Okay, well, what it means to be closed under addition is I have to take two vectors in W, and I need to show that their sum is in W. That's what it means to be closed under addition. Okay. So, is that true? If I take two vectors in W, is it the case that their sum is in W? Well, if F is in W, what it means for F to be in W is that F of M is equal to 0. Look at our rule. That's what it means for a vector to be in W. Likewise, what it means for G to be in W is that G at the midpoint is equal to 0. So we're given F of M is equal to 0 and G of M is equal to 0. We're taking that as given. Our question is about F plus G. Does F plus G have this same property? So, in other words, does F plus G have the feature that when I plug in M, I get 0? Well, we're going to test that by taking this F plus G and plugging in M. And we hope we get 0. So I'm going to compute F plus G of M. All right, well, here's our definition of how to evaluate the vector sum F plus G. Conveniently, we already know that F of M is equal to 0. And likewise, we know that G of M is equal to 0. And so we have 0 plus 0, which is 0. And so as required, whenever you have two vectors in W, it does indeed follow that the sum is in W, and that's what it means for a set to be closed under addition. Okay. All right, so we're halfway there. We've checked that W is closed under addition. Next question, is it closed under scalar multiplication? Well, we're going to go through a very similar process. We're going to assume that we have a vector in W, and we're going to try to show, hopefully, that a scalar multiple of it must also be in W. This means that if this were true, we would detect that by evaluating this and getting 0. So we evaluate it. How do we evaluate this function called CF? Well, we have rules for how to evaluate this scalar vector product function CF. And this is how you evaluate it. Conveniently, F of M, already known to be 0. C times 0, of course, is 0, and therefore, as required, CF, as this same property, that it's 0 at the midpoint, and therefore, as required, CF is in W, and therefore the set is closed under scalar multiplication. Okay. So what we've done here is we have shown that this is a subspace of capital F, a known vector space. Of course, a subspace is, by the definition of subspace, also itself a vector space. So in fact, I've confirmed that this W is a vector space. And the beautiful thing about this process is I did not have to go through and enumerate all 8 of the required properties of a vector space. I let that be done for me automatically by the fact that I know that we're looking inside of a known vector space and using the same operations as a known vector space. So we very cleverly avoid most of the work by showing not directly that W is a vector space, but by showing that it is a subspace of a larger vector space. Okay, so let's see some more examples. The collection of all continuous functions on an interval from A to B. Well, this is clearly a subset of capital F, the collection of all functions on that interval. This set is just the ones that are continuous. And in order to decide if this is a subspace, we need to ask, is this closed under addition? Is this closed under scalar multiplication? And, well, in fact, these are some old known facts about continuous functions from single variable calculus. An old fact from back then is that the sum of 2 continuous functions is a continuous function. And a scalar multiple of a continuous function is a continuous function. Of course, in a single variable calculus class, it's not said in the language of vector operations, but nevertheless, fact remains. So, by those old single variable calculus facts, this set here is closed under addition, it's closed under scalar multiplication, it's a subset of a known vector space, therefore this is itself a vector space, and it's a vector subspace of capital F. Likewise, B, the collection of differentiable functions, and we have some similar facts from single variable calculus. The sum of 2 differentiable functions is known to be differentiable, and likewise scalar multiples. So this is a vector space and a subspace of capital F. In fact, furthermore, this one's a subset of that one. Certainly every differentiable function is known to be continuous. Okay. All right. So here are some others. These are interesting. Dn, collection of functions that are at least n times differentiable. So it has an nth derivative. I'll put that n up here as a superscript. Not hard to show that if 2 functions have an nth derivative, then their sum has an nth derivative, again by facts from single variable calculus. Okay. Likewise, this collection of functions that not only have an nth derivative, but where that nth derivative is continuous. And that's a slightly stronger requirement. It is not the case that just because a function has a derivative, that derivative is necessarily continuous. It's a little bit stronger of a requirement. And it turns out that these subspaces nest in this wonderful way. So this says every differentiable function is continuous. This says that every continuously differentiable function is differentiable. I mean, that's sort of an immediate thing. If its derivative exists and is continuous, then certainly its derivative exists. Now let's look at this one. This says that a function is twice differentiable. In other words, that its derivative is differentiable. This says merely that the derivative is continuous. And certainly we know that every differentiable function which is the derivative of another function, is also continuous. So this pattern continues. So D1 is a subspace of C0, C1 is a subspace of D1, D2 is a subspace of C1, etc. And we have this sequence of nested subspaces that are increasingly subsets of each other. Okay, you might say down at the end of this list, so to speak, is C infinity. This is just the collection of functions that are infinitely differentiable. And that sounds like a foreign idea, but in fact, most of the functions that we deal with most of the time have this property. Take sine x, for example. You can take all the derivatives you want. The derivatives are all continuous and furthermore differentiable, and there's just no, you can take as many derivatives as you want. It has infinitely many derivatives, as do, well, most other functions that you deal with, exponentials, etc. Okay. And furthermore, notice that because the requirements of this subspace are stronger than the requirements of these subspaces, this C infinity is a subspace of all of the previous. Okay. Then there's a collection of all polynomials. Well, that's a subspace of C infinity because, well, of course, every polynomial has this feature of being infinitely differentiable. So these are increasingly smaller vector spaces. And the interesting thing about it is you consider the collection of all polynomials. Well, this is, in fact, an immense vector space. All polynomials. Notice this does not say polynomials with integer coefficients. This is all polynomials of any degree. Linear, quadratic, cubic, quartic. This is immensely large vector space. And it is the smallest of all of the vector spaces in this list. So that tells you a little something about how big this vector space is, the vector space of all continuous functions. It's way bigger than an enormous, in fact, it's in some sense infinitely bigger than an enormous vector space. That's a fun little discussion. The student should be aware of the fact that this notation, these two notations are in common use. These are not arbitrary. Students should make sure to remember what this vector space is and what that vector space is, and likewise these, and likewise these. Okay. A couple more examples. Let's consider the span of a collection of vectors in a vector space. Well, it's not hard to show that this is a subspace of that vector space. I'm going to leave this as an exercise for students to do on their own. Remember, all you have to do to check that this is a vector space is show that it is closed under addition and closed under scalar multiplication. So check these two things. Check that if you were to take a linear combination of these vectors and another linear combination of these vectors, check that when you add them, the result is also a linear combination of these vectors. And likewise, check that if you take a linear combination of these vectors, that when you multiply by a scalar, that the result is a linear combination of those vectors. And good practice to think through and good practice to write down. Okay, here's another one. Let's consider given a matrix A, an M by N matrix A. Consider the collection of homogeneous solutions for that matrix, thought of as a coefficient matrix. Well, that's a collection of vectors in Rn, this being n, and we're going to confirm that this is in fact a subspace of Rn. So, said differently, More importantly, this is a vector space. The collection of all homogeneous solutions is a vector space. And the way we're going to get to that conclusion is by showing it's a subspace of Rn. So, again, 2 requirements. Step 1, need to show that it's closed under addition. Now you'll notice I've been a little bit more compact in how I've written this down now that you've seen a few examples of how these look. I'm going to write the arguments a little bit more compactly. So we're going to start by assuming that x1 and x2 are in this set, and then we're going to show that their sum is in this set. So that shows that it's close under addition. Well, x1 being in this set tells me that ax1 is equal to 0. Similarly, x2 being in that set tells me that ax2 is equal to 0. Alright, now question is x1 plus x2 in this set. Does x1 plus x2 satisfy that property? Well, I would need for this to equal to 0. I would need for that to equal to 0. And you see that that is the result that we're going to get to. So how do we compute that, though? Well, first, we use this distributive property of multiplication of matrices. Then I cite the fact that ax1 is known to be 0. Why? Of course, because x1 is in H. And then I cite the fact that ax2 is equal to 0. Again, this time, because x2 is known to be in H. And 0 plus 0 is 0. So, as required, that satisfies that property, and therefore the sum is in H. And therefore this is closed under addition. So a bunch of words to be said, but those ideas are all represented in this relatively compact argument. Likewise for scalar vector multiplication, you have a vector in H. You need to show that a scalar multiple of it, all scalar multiples of it, also in H. This means that. This would be confirmed by that. So we compute this. This is true because of properties of matrix multiplication. By assumption that's equal to 0. And C times the 0 vector is the 0 vector as required, so that's in H. And so therefore H is closed under scalar multiplication. So we've checked closed under addition, closed under scalar multiplication, and therefore it's a subspace.